So a very warm welcome to this afternoon's NRICH live webinar. My name is Liz Woodham. I'm a member of the NRICH team, and I'm delighted that I'm joined by Charlie Gilderdale. Hi, Charlie. And by Ems Lord, who's the director of NRICH. And together we hope that we'll enjoy doing some mathematics with you this afternoon and considering how the tasks can be used with your learners back in the classroom. Before we get going properly, I'd like to say a very big thank you to Trinity College, who fund these events, which means that you, the participants, don't have to pay. So thank you very much to Trinity. At various points, we might ask you to contribute via the chat as we work on tasks together. So we'd love you to do that, please, to get a bit of a conversation going on the chat. Don't worry about posting ideas that are completely formed. We always like you to post emerging thinking, and then we can take it forward as a whole group. So thank you. So this afternoon, we are gathered together to focus on curiosity. Charlie and I have been giving this quite a great deal of thought in the sort of time running up to this webinar. And what we're hoping to do is to share with you some resources that we hope will help you to nurture students' curiosity. And in particular, I'd like to share with you an article where we've gathered together our thoughts. So let me pop that up on the screen to begin with, just to give you a flavour, and then I'm going to hand over to Charlie. So I'm hoping that you can see an article up on the NRICH site here. It's called Nurturing Students' Curiosity. This is accessible from the current features, which you can get to both from the primary teacher homepage and the secondary teacher homepage. So it's linked right at the very top. Rather than give you a lot of information straight at the beginning, what we're going to do is launch straight into a problem, and then we can use that problem in order to consider how we might help students and build on their natural curiosity. So Charlie, I'm going to hand straight over to you to get us started, please.
Well, since you're sharing your screen, I think we might as well ask you to scroll down a little bit down that page. And now at the bottom there, you'll see that there's a link to a problem called the number jumbler. So we're not going to spend very long on it because I think we might have talked about it before, but just for the sake of those who've never seen this before, it might be quite fun just to do it, to show everybody once what's involved. So can you maximize your, okay, if you can scroll, yes, I can't see the bottom yet. Now I can. Yeah, brilliant. Okay, so the task that we're asking everybody to do, and ideally we'd like everybody to have a go at this and then be able to tell us in the chat what happened. So we'd like everybody to choose a 2-digit number. So 45, 17, 94, 22, any 2-digit number, anything between 10 and 99. And we'd like you to then add together your 2 digits. So I'm going to choose a nice easy one like 24 because 2 and 4 are really easy to add. So take your 2-digit number, add the digits. And when you've done that, subtract the total from your original number. So in my case, I'm going to have to subtract 6 from 24. So can everybody have a go at subtracting the total of their digits, sum of their digits, from the original number that they thought of? Once you've done that, can you please take a look at the grid on the right of the screen? And you should find that your answer to your subtraction is somewhere there. You started with a 2-digit number, you you had a subtraction, you carried out a subtraction. So the answer is going to be somewhere between 0 and 99. Can you have a look and find your answer? And then we'd like you to look at the icon, which is just to the right of your answer. So if your answer was 51, you'll be looking at a heart. And if your answer is 67, you're going to be looking at a smiley face. So I'm told that for this to work, we all need to be really concentrating and sort of hypnotizing powers. And if we can all stare at the icon, then Liz, I'd like you to jumble them all up together, please, and see what happens. Oh, an ice cream cone with ice cream. I wonder whether everyone could put in the chat what they were staring at when they were looking at the grid that was on Liz's screen. Were you looking at a heart? Were you looking at a smiley face? Quite a few people seem to be looking at an ice cream. In fact, it looks like everybody except for one person was looking at an ice cream. What were you looking at, Liz?
I was looking at an ice cream too. In fact, it was very nice because it's very hot here in Cambridge and it was making me, you know, quite appealing, quite appealing.
So we'll come back to this problem later on. And just in case I forget to mention it later, we're not doing this because we want you to think maths is magic and mysterious. Actually, we're doing this because it is surprising that almost all of us were looking at an ice cream, but there is a fairly simple explanation to why this is. So we wouldn't want to carry out a magic trick or a trick that looks like magic and adds to the stereotype that maths is mysterious and incomprehensible. So we will come back to this problem at the end, and hopefully you'll feel that the explanation is accessible. But we thought it would be quite a good way of starting the afternoon to give some idea of the kind of hook that we can sometimes use to kickstart a lesson. So perhaps, Liz, if you go back to the Nurturing Students' Curiosity, and we have a look at that section where number jumbler was. Oh no, let's talk about all of them, and then we can look at why number jumbler is where it is. But I think I'm going to leave you to do that.
Okay, thanks, Charlie. Yes, so I guess we're very aware that young children are inherently curious. They constantly ask questions, and somehow as they get a bit older, perhaps that curiosity, I was going to say evaporates, that makes it sound like it disappeared completely, but perhaps somehow it becomes, we value it less. And in maths lessons in particular, I wonder whether potentially students think that it's not a place to ask questions, that actually curiosity is actively discouraged in a maths lesson. And yet, of course, we know that a good mathematician is curious. A good mathematician asks questions. So what Charlie and I have done here is we've thought about sort of 7 categories, if you like, 7 ways in which we think that you might be able to nurture that natural curiosity and build on it in a mathematical context. Now, if I scroll down sort of briefly, you can see that on this page, we've linked, each blue link is a different NRICH task. So if you looked at all of those tasks, you would see that they cover a wide age range. Now, of course, in this afternoon's webinar, I'm afraid we're not going to get a chance to look at all of these tasks. So what we've tried to do is choose a few to work on with you to exemplify some of these categories. But of course, you can go back to this article and pick out the tasks that are relevant, particularly for your children, for your learners. So Charlie, you mentioned the number jumbler, which you've kicked off with. As you say, it hooks us in by giving us that element of surprise. Oh, I wasn't expecting that. Wow. And we've put that, if we look down these bullet points, you'll see that number jumbler comes here. And this category is exactly that. We're offering a surprise, but actually then challenging students to explain what is happening. Why has that surprising result come about? And I think Charlie and I feel that this category that we've just introduced via the number jumbler has quite a few links with the two preceding ones. Would you agree, Charlie? So presenting unusual situations and contexts and intriguing and puzzling contexts. These three sit quite nicely together, and we will look at some examples further along. Charlie, would you like to say anything more about those particular categories? Oh, you're on mute.
Sorry. Yeah. Those tend to be the more obvious ways of tapping into students' curiosity. But we've got the sort of 3 bullet points at the very top, which we think are equally important. So as Liz was saying, creating a culture which encourages students to ask questions and experiment, and offer them contexts in which questions might crop up. We often, when we're working with students, say, what do you think a mathematician might ask themselves next? So that students realize that to be a good mathematician doesn't just require students to answer questions, but also to ask good questions.
Exactly. So shall we go on to another task, Charlie? We've chosen a task to share with you now that we believe is accessible with fairly young children, but has the potential to actually challenge way beyond learners' early mathematical experiences. So I guess it's a typical low threshold, high ceiling task that you may have heard us talk about that label before at NRICH. I'm going to open a new tab to share with you, but what I'm going to do quite quickly is open the new tab and then change the size of my browser so you can't read all the text. So don't look too carefully now. Oh no, and then I got stuck. Don't read. Have a slurp of your tea. Okay, there we go. Now you can look at the screen. So we've got here a task that, as I say, is very accessible to quite young children. And what we're going to do is we're going to have a go at it with you. Now, obviously, you being very sophisticated mathematicians will be able to solve this in ways that perhaps, depending on the age with which you work, won't be necessarily accessible to them. But let's have a little look together, and we'll invite you to post in the chat in a second. So we've got these two friends, Francis and Rishi, and they've got a bag of lollies, and they share them out between them, and they have one lolly left over. So just have a little think about, please don't post anything, but just have a little think about that scenario. So they've been shared, all the lollies shared between the two of them, and there's one left over. Now, unluckily for them, 3 of their friends come along. Let me make this window a little bit bigger. So this means there are 5 of them all together now, and Francis and Rishi, being very kind, they decide that they'll put all the lollies back in the bag and share them out between all 5 of them instead. And when they do that, they find that there are 2 lollies left over. So I'm sure you can predict what the question is going to be. How many lollies could there have been in the bag? Now, at this point, I'm just going to give you a little bit of time to have a think. You could not only, first of all, have a go yourself, but then think about the learners that you work with. How do you think they might approach this task? So just a couple of minutes.
It's interesting that the many different ways that people are describing the solution.
I absolutely agree, Charlie. I was just thinking the same thing. It's also nice that some of you are posting, as Charlie says, different ways of describing the solution. Some of you have offered some suggestions about what you think learners might do, which is great. So those two things complement each other. I'll just give you half a minute more. Thank you all. So I think I can see, as you say, Charlie, I can see a whole range of contributions from you in the chat, all of which are extremely helpful. So I think some people are suggesting that learners might want to use some concrete apparatus to have a go. Absolutely. So you could, I did get out a few nice coloured counters in case we wanted to play for that. Some of you were suggesting that possibly learners might come up with a solution to start with. Somebody mentioned perhaps they'd find a solution 7, because that was the scenario where everybody got 1 lolly. So maybe that would be a starting point for some children. Somebody else said, well, I know it's got to be an odd number straight away. So that was a sort of a leap in, that I know something straight away before I consider the 5 people. And then others of you have straight away articulated a generalization, which is to do with multiples of 5, and you phrased it in all different ways. Charlie, is there anything that you'd like to chip in terms of what people have contributed before we look at what's on the site?
No, I think you've covered everything here. Yeah. Okay.
So on NRICH, what we've done is we have offered, what we suggest is using this task with children is to give them a chance to have a think themselves, maybe on their own just for 30 seconds and then in pairs, and to begin to work towards a solution, but actually not necessarily give them time to find a full solution. And instead, on the site here, we've offered some examples of children's thinking. Now, these are all based on previous solutions we have received to this problem. So these are not randomly made up. They are based on genuine the way that children have genuinely worked on this task. So Sarah, Danielle and Sally do a little bit like we said earlier, that they found some solutions. So they've started with one solution. They said, we noticed that 17 works and we noticed that these work. So perhaps they might go down a route of thinking, oh, I can see a pattern here. Is that pattern always going to hold? I wonder why. Poppy has been quite systematic, and she's approached it from the point of view of, if I'm sharing out these lollies between 5 children, what if they had 1 each? What if they had 2? What if they had 3? She's listed all the possibilities. What she hasn't done yet is thought about the odd. So for the fact that she knows it's got to be odd because of the sharing between 2 at the beginning. Phoebe and Alice, they've done some nice recording here, and somebody mentioned possible other ways of recording. So here we've got a number square, 100 square, and I'm not sure how clearly you'll be able to see this, but they have shaded in a sort of a browny red colour all the odd numbers, and then on top of that they've also they sort of hashed in green the numbers that give 2 left over when shared between 5. And so of course you can tell from the number square, the 100 square, straight away which numbers satisfy both of those conditions. So we offer those to children, and I'm thinking, okay, how could you take this and go further? So this links to exactly what Charlie was saying earlier about that hooking children in. The curiosity is, oh, I can do this in more than one way. I didn't think of doing it like that. Is that going to work? Am I really going to be able to use that way to work to a full solution? How? Now, as we were working on this problem, Charlie had some really lovely suggestions of how we could take this further. Charlie, can I hand over to you?
Okay, if you want to scroll down a bit, then I was thinking, well, we could ask, well, would it be possible to work out how many lollies there were if there was 1 left over initially, and then instead of 2 left over when you have 5 children, you had 3 left over or 4 left over. So we were just curious about whether there was always a solution.
Yes.
So we'd like to give you this follow-up task, which is to imagine that there are 3 friends to start with. It's the bit that's in bold at the bottom of Liz's page. Sorry. So there are 3 friends to start with, and then there are 5 friends. So how many lollies could there be in the bag if there was 1 left over to start with and 1 left over when there are 5 children, or 1 left over to start with and 2 later, or 1 left over to start with and 3 left over whenever. So in the chat, I'm going to suggest how people might write the answer. So for the problem that we've looked at just now, one way of writing it could be that I had 1 left over to start with and 2 left over later on, and my answers were 7, 17, 27, and so on. And that is what I've just stuck on the chat.
Oh yeah, nice. Okay, so that offers us a notation. Yeah.
So 1,2 means I had 1 lolly left over to start with, and then I had 2 left over. And because the original example had 2 children and then 5 children, I think 7, 27, 7, 17, 27, and so on. So our challenge to you is this. Could you write in the chat what you think the number of lollies is for 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4. That is because there are 3 friends to start with,
yeah,
and 5 later on. Is there always a solution? And you might want to use one of the strategies that you saw Liz describing, or one of the strategies that was mentioned in the chat earlier on. I'm relieved that my instructions made sense to at least a couple of people. So Yamuna and Vali have suggested that if there's one left over at the start and then one left over when all 5 children are together, there could be 16 lollies. One more than 15. If there'd been 15, there'd be none left over in either case. And by having 16, we've got one left over. And Yamuna has given us a whole family of solutions. And Jacqueline has suggested that the general case for the first one, I'm assuming, is multiples of 15 plus 1. And that sort of makes sense because multiples of 15, nobody would have anything left over. There would be no lollies left over when there were 3 children. There'd be no lollies left over when there were 5 children. So whether you have 15 or 30 or 45 or 60 or 1,500 lollies, there'd be none left over. But if you add 1, there'll be 1 left over. So it's quite nice because the 1-1 example is the easier one to start with. And then 1-2 and 1-3 and 1-4, slightly trickier.
And of course, just to emphasize, as Charlie said, although we might be approaching it in a particular way, we might expect children to be doing it in a different way, using any of the strategies that we've seen on the site here, a slightly more trial and improvement type approach, finding some solutions and looking for patterns. We wouldn't necessarily, depending on their experience, we wouldn't expect all children to be able to jump in straight away to express their solution in the way that some of you are doing. I think it's important to say that. Yes, and that yeah, I think Vali, you've sort of encapsulated in your comment what you might hear in a classroom. Oh, there are more. Oh, let's look for a pattern. Yeah, that's certainly the first stages potentially.
I've got a question for Yamuna. I think there may be a solution between your 13 and 43, and there may be a solution between your 43 and 73.
Mm-hmm.
I think you did say something about students working in pairs, Liz.
I did, yeah, yeah.
There'd be interesting discussion.
Yes, there definitely would. That sort of model of think, pair, share. So giving everybody a chance to think on their own first can be quite important, and for some children is really valuable. Then sharing their ideas with a partner, and then inviting contributions in the whole group.
What's also quite nice is that I imagine some secondary teachers are writing algebraic expressions,
yeah,
which shows that this task can challenge students to work algebraically and express algebraically the solution. While with primary students, playing around with the numbers, testing the numbers, using a 1 to 100 square,
Absolutely.
like two of the children did on your page, offers a slightly different kind of challenge. But it seems to me the problem is equally valid for students
Absolutely.
of different ages.
Yeah.
And when we talk about low threshold, high ceiling tasks, that that makes this problem hopefully accessible to the majority of children,
yeah.
but offers an extra challenge for those who are ready for it.
So I think this problem offers, I think it, for me, it sort of exemplifies a couple of different ways of potentially building on students' curiosity. One is by offering them a range of strategies, so that, you know, getting that sense of, oh, as I said earlier, oh, I didn't think about trying that way. Yes, let's have a go at that. So hooking me in that way. But then the other idea, what we've come on to here, is another of our categories, perhaps about a having found a strategy, it then being applicable in a much more generalizable sense, which is really rather nice, I think. And exactly as you say, Charlie, perhaps is where you might go with older students who've got more mathematical experience. Some of you have found some very comprehensive solutions. Yes, and Adam points out that he wrote the two sequences and then found the common multiples. Yeah, absolutely, and I think many students would do that as well. Charlie, I wonder whether we have put another question at the bottom of here. Can
I just ask Liz?
Yeah.
Because Paul has said that for 1-5,
yep,
there are no solutions. Sort of one left over, and I'm not sure I agree with him. Now, I'm slightly worried about saying this, because I know Paul. I think he's a much better mathematician than me. But
you couldn't have. Surely that's just because you couldn't have 5 left over because.
Well, I mean, you could have 5 left over and give them back. I could treat 1-5 the same as 1-0, Liz.
Yes, yes.
And what I don't know is whether Paul is saying there are no solutions to 1-0.
Oh, I see what you mean.
Because 1-5 is, well, there are 5 left over, okay. But
Paul says that's what I meant, as in 1-5 is the same as 1-0.
I think there is a solution to 1-0. Okay, and
so what we mean.
Yes, and Adam has got suggested that 10 is a solution, and I had 25 as a solution. Yeah, okay. So if we had 10,
yeah,
when there were 3 children, there would be 1 left over, and when
yes,
there were 5 children, there'd be none left over.
There'd be none left over.
Okay.
So I think Paul, we agree.
Yes, good.
What you're saying. Yes.
Okay. I mean, we haven't done any of the 2, 1, 2, 2, 2, 3, but perhaps we've spent long enough with 3 children and 5 children. Yeah. So I'm curious about the very last bit of the question. Let's all work on one last question.
Yeah.
Can we imagine that there are 4 friends to start with?
Yep.
And then later on, 2 more join them. And the 1-1 example is too easy. So let's just start at 1-2.
Okay.
Well, how many lollies could they have if there was 1 left over to start with, and then when they were the bigger group, there were 2 left over to start with?
Okay, let's have a think about that. Sorry, I tried to post then the problem that Charlie suggested, and I've managed to post it in 2 separate messages, which is not very clever of me, I have to say. So just to echo again, 4 children, there is 1 lolly left over, 2 more children arrive, and this time there are 2 lollies left over.
I think we've got an example of resilience here, with Valley saying,
yeah,
no solution so far.
So far, yeah, not yet.
Not giving up.
Mm-hmm. So there's a suggestion of 17 or 33. I think 33 definitely would have 1 left over when shared between 4. But then when shared between 6, I'm not sure that there would be 2 left over. 17. Yeah, I'm not sure for 17. There's 2 left over when shared between 6.
Okay, I think a few people have spotted why we've asked this question.
Yeah.
And as Vali and a couple of others have said, it's impossible, because if you're going to have 4 friends and 1 lolly left over, then there must be an odd number of lollies. And if you add 2 more friends, you have 6 friends. And if you share lollies out evenly, and then there are 2 left over, you must have an even number of lollies. So you had an odd number of lollies to start with, and then an even number of lollies. And we're assuming that you got the same number of lollies throughout. So an interesting question to ask students might be, can they come up with other examples of number of children and number of lollies left over where it's going to be impossible for things to happen? And
that's right.
6 and 4 have common what am I going to say? Both multiples of 2, and so there are going to be some problems. Can they use that to help them find other examples? Yeah. Right, Liz, it's sort of 4:45. And
yes, I think we've got another problem which follows on really nicely from this one, which also it kind of offers a different way to develop and to nurture curiosity. Charlie, would you like to share your screen at this point? I'll stop sharing.
Okay. Okay, let me tidy up my screen. Can you see Charlie's Delightful Machine?
Yes, I can, Charlie. Oh,
Okay.
hang on. Yeah.
So let's start with 0 or with 1. Okay, so there are rules that apply to switching the yellow, the red, the blue, and the green light bulb. So I can keep adding numbers. So 3 switches the blue light on, 4 the yellow and the green, 6 the blue. So 3 did the blue and then 6 lit the blue. So it might just be that multiples of 3 light the blue. Let me just check. Yes. So 9, and I suspect 900 might light the blue, or 45. Okay, so that's good. But other rules determine whether the yellow light bulb switches on, or the red, or the green. So let's look at the green, for example. That's come on at 10 and at 16. So if we carry on adding 6s at 22, so it always seems to be 2 less than a multiple of 6. So 34, yeah, 2 less than a multiple of 6. And we can see that sometimes all 3 light bulbs switch on. And the question is, can we get all 4 light bulbs to switch on? So we've got 28 to switch all 4, and sorry, all 3. I think it was only the blue one that was missing, but 48 switches these 3. I haven't seen all 4 switch on yet. So 48 didn't switch the green one, but somebody's got their microphone on. Okay. So I don't know, Liz, whether we want to give everybody a couple of minutes to have a go on their own browser, because if I refresh, there'll be different rules. And I don't know whether they've got enough time to do this. But actually, given that we're going to go back to Number Jumbler, perhaps there isn't enough time. But we'd like to talk about Number Jumbler, wouldn't we? So this is another opportunity to get students working, maybe collaboratively, working out the rules for when the yellow light bulbs go on, the blue ones go on, the red and the green, and then trying to work out when we can get them to match. And it feels like it's a very similar kind of thinking that we carried out in Lots of Lollies.
Yeah, I agree.
So we normally, I mean, when we wrote this, it was sort of for secondary age students, but it's interesting that you wrote Lots of Lollies for primary age students. And we're sort of saying that actually some of the thinking can be both carried out by primary and secondary students, and the two together offer a chance to develop very similar thinking.
Absolutely. Yes, and just go on, Charlie.
No, I was going to say, we do have a link to this on this. Have we put a link to this page on the chat, Liz?
Yes, Ems did right at the beginning, but why don't I put it up again? Yep. Here we go.
Yeah, while Liz is doing that, I'm just drawing attention to the 7 bullet points that Liz talked about. And we've talked about Lots of Lollies as a problem that welcomes diverse approaches. We've just been talking about Charlie's Delightful Machine, which is sort of a puzzling kind of context. And we promised to go back to the Number Jumbler in case people go away thinking, maths is mysterious and magical and no one's going to understand it. So here we go. Let's have another go at the number jumbler, shall we? So, can you see that, Liz?
Yeah.
Okay, so just like before, you might want to choose a different 2-digit number this time. On the other hand, you might want to choose the same one. Okay, choose a 2-digit number. We'll go a bit faster this time. Add together the 2 digits. Instead of 24, I'm going to choose 25 because that's still an easy sum. And then when you've added your 2 digits together, subtract that from your original number and look for your answer on the grid. And then we need everybody's mental powers staring at this and see what happens. I'm going to jumble up all the images, try and remember what image you're looking at. Here we go. So in the chat, can you say what image you were looking at? Were you staring at an ice cream cone again, or at the heart, or at the smiley face? And it looks like the majority of people were looking at the sunflower, which is the one I was looking at. So I'm curious, for those of you who were staring at a sunflower, could you write down what number you got at the end? So I'm not interested in what number you started with, because that was all fairly random. But what number did you finish with after you added your digits and subtracted the total of your digits from your original number? Ha! Vali said there's a pattern. There is indeed. So this is a nice example of where students working together, doing this several times and noticing what's happening. Noticing, for example, that every time I refresh the page on Number Jumbler, the multiples of 9 have a different image. So the first time, all the multiples of 9 were ice creams, and this time all the multiples, and then the second time, all the multiples of 9 were sunflowers, and this time on my screen, all the multiples of 9 are smiley faces, including a few numbers like 59, which are not multiples of 9. Why do you think that's got a smiley face, Liz? Oops.
I think that's a red herring, Charlie.
Okay.
I think that's to kind of make us think, ooh, but this one does too. Oh.
And Graham's noticed that 90 and 99 do not have smiley faces. Why is that, Liz?
I think that is because doing the calculation that we did, it is impossible to get 90 or 99. Because you were very clear that we started with a 2-digit number.
So if I started with a number in the 90s,
yeah,
like 94, when I carried out my subtraction, I'm going to end up with 81. I can't end up with 90. I'm going to end up subtracting more than 9. So I'm going to end up with less than 90.
Yeah.
Good.
Yeah. Yeah.
Yes. And Adam is noticing, yes, we're not.
Exactly, Adam. Yeah.
Yeah.
To make the pattern less easy to to identify. Yeah.
Less obvious, yes. So actually there are quite a few numbers like 92 and 3, which have got smiley faces, and 40, oh no, it's not 46, 46 is, and 40. Okay, so so we know that you always get multiples of 9.
Mhm.
I suppose the question is, why do you get a multiple of 9?
Yeah.
Would anyone like to have a go in the chat to try and explain why you get a multiple of 9? And again, it doesn't have to be an algebraic explanation.
No.
So algebraic explanations would be very welcome from secondary age students. Actually, yeah, Graham's written the kind of explanation I would hope many secondary students would write.
Yeah.
But Pavla has written something which sort of bridges the gap between primary and secondary, it seems to me. Because if I have a number like 42,
Yes.
I've got 4 tens and 2 units.
Yeah.
And then I'm going to have to subtract a 4 and I'm going to have to subtract the 2.
Yes.
I mean, I was saying add the 4 and the 2 and subtract it all at once.
Yeah.
But you could imagine saying,
yes.
Well, I've got the 42. I'm going to subtract the 2 because I'm going to subtract the units. That's going to leave me with 40. I'm also going to subtract the 4. So instead of having 10 fours, I'm going to have 9 fours. And what Pavla has written there, which is, yes. I've got sort of, imagine the numbers written M, N. I've got 10 lots of N and an N. And I'm going to subtract an M, and I'm going to subtract an N. And I'm going to end up with 9 lots of. So what's quite nice about that is that whatever number I end up with, let's say 50, if whatever number I start with, let's say 51, that's telling me I'm going to end up with 9 fives.
Yes.
9 times the number in the tens column. Yes. I'm going to end up with 45.
Yes.
So I was messing around with 24s and 25s earlier on. I ended up with 9 twos. I ended up with 18 in either case. Right.
Yeah. That you're right, but that's a rather, I mean, it's I guess what it is that it's the simplified expression that Graham has written, but actually it seems to reveal the underlying structure a bit better somehow, doesn't it? Yeah, absolutely.
It's nearly 5 o'clock, according to my
5 o'clock. We should, and I just to say very briefly, even if students cannot express, as Charlie said, even if students cannot express that algebraically, in terms of symbolically, if you like, they can still participate in that algebraic thinking and express the value of a number as being 10 lots of the tens digit and the number of ones digit, and the total gives the value. So even younger children can access that thinking, even if they haven't met formal algebraic notation. So Charlie, thank you. Let's go back to the article. Go on.
You could also almost do sort of proof by exhaustion.
Yeah.
If you start with 21, what do you end up with? 21 minus 3 is 18. If you start with 22, 22 minus 4 is 18. If you start with 23, 23 minus 5 is, oh, whenever I start with in the 20s, I seem to end up with 18.
Yes,
what happens when I start with the 30s? Oh, I always end up with 27. What's that? And so you can, sort of, without having to do every single example, you could. Right, I've gone back to the Nurturing Students Curiosity page.
Yes.
Did we ever mention Albert Einstein's quote? I have no special.
We didn't actually, no, but it's rather lovely, isn't it?
But I just wanted to draw attention at the bottom. We've also added a few resources for those of you who are really curious about curiosity, that we think might be interesting. So we often talk about Alan Wigley's article about models for teaching maths, and he often suggests, suggests in that article that starting a lesson with a problem, with a question, with a challenge is a really good way of starting. Peter Liljedahl's 14 Practices for Building Thinking Classrooms has a couple of practices which are linked to motivation and curiosity. There's a video of a lesson that was carried out some years ago with a younger version of Charlie and a younger version of my ex-colleague Alison, which starts with a question. So and then there are other people like Dan Mayer, and I can never remember the name of the person who does inquiry maths, Andy, I think he is, who've got also resources. And there are more resources than what we think and why we think it. And finally, as a sort of homework, questions to consider with your colleagues, I suppose the challenge after all this is, how do you create a culture in your classroom where students are confident to ask their own questions? And how do you adjust your lesson plan to accommodate students' own mathematical questions? And of course, it may not be possible to do in a lesson. It might be something that one returns to. But it seems to me that those are two interesting questions to go off and talk to colleagues about.
Absolutely.
I think
Thank you, Charlie.
I've said enough. I will put...
Don't stop sharing actually yet, if you don't mind. Would you mind just scrolling to the top, Charlie? And just if you go to the events page, just so people know that this recording will eventually be put up onto, if you look at there we've got information about today, but there's a link to all our previous NRICH Live events with their recordings. So the recording from today will go at the top of that page there in due course. So
the last one we did was that one in April about quadrilaterals.
Yeah. That's right. And really the last thing to say is we presume that you will have found out about today, either possibly because you signed up for our email mailing list, maybe you follow us on Twitter, but do look out, if you're not already following us in one of those two ways, please do sign up. And watch out for a newsletter and information that will come fairly soon about the summer challenges, which we hope to create, which we tend to do every year. This year will be no exception. We're hoping to pop up 40 challenges from starting on the 10th of July, every weekday through to the end of the summer holiday, which takes us to the 1st of September, I think. So do mention those to your students before you break up for the summer holiday, if you are in a country that has a long summer holiday. I think that brings us to the end of today. I'm sorry that we've run over very slightly. Ems has been very efficient at posting the feedback form link in the chat. We really do appreciate your feedback, so do take a moment to fill that out for us. We would very much appreciate it. I think it's time then to say goodbye. We hope you enjoy nurturing your students' curiosity.